Let's now discuss the other circuit, which is the charging circuit. So in this case, you have a capacitor that initially we will assume has no charge whatsoever, and it's now being charged by attaching it to a battery via a current limiting resistor R in series to it. So from a physics perspective, what really happens is the following. The negative side of the battery has got more electrons than the positive side of the battery. So what's really going to happen is that electrons are going to get transferred from this side and get moved to a higher potential and go to this side. From here, I mean, the electrons get transferred from here and then they move there. So you're going to get a electron current that's going to be from here in this direction, in a counterclockwise direction. But according to Ben Franklin convention, we're going to think of the current as being the opposite of that. In other words, we're going to assume the current is carried by positive charges instead of negative charges. So the fictional account is that positive charges, which are a surplus of on this side of the battery, go and deposit themselves on this plate, making this plate eventually positive, and negative charges, which are excess of on this side of the battery, go and deposit themselves there. That's the fictional account. The real account is what I told you first. So how does this pan out in terms of KVL? Well, we can use any loop. Let's take this loop. So I'm going to write the Kirchhoff voltage law for this circuit. Because I've taken this direction of loop travel, I have to maintain that convention. Let's start from the battery. I'm going from positive to negative, so I'm losing potential. So that's negative E. And then I have a gain in potential because I'm going from the negative to the positive side of the capacitor. So that's going to be plus Vc. And then I'm also going to be going against the resistor, which means I'm climbing the potential hill. So plus Vr equals 0. Or in other words, it tells us that the total EMF equals Vc plus Vr. Now I just used a word, I call the battery's voltage the EMF. What I really mean by that, let me take this opportunity to finally tell you what the difference is between EMF and voltage. Every battery, such as the one you get in a store, has actually got a resistance in it. So the battery comprises, if you look at the inside of the battery, a way of writing the circuit diagram for this battery is that this side will be the earth, and then inside there is actually an internal resistor known as little r, and then there is also a pure source of EMF E. Now when you actually test the voltage of a battery using a multimeter, you will find that the battery's voltage is bigger than 1.5 volts. Even if the battery is billed as a 1.5 volt battery, it's actually bigger than 1.5 volts, because what the voltmeter is measuring is the resting potential energy with no current flowing through it. The voltmeter is such that its effective resistance is infinite, so it can actually measure the true EMF of the voltage cell, which is always going to be higher than the billed voltage. Once you use this battery in a typical circuit application, and again the word typical means that the manufacturer has to gamble a little bit as to how this is usually used in a application, the internal resistance is such that the total voltage is going to be the true voltage minus the current through the internal resistance times the resistance by Ohm's law, and that voltage is always going to be less than the voltage you measure, the resting voltage you measure through the multimeter. Anyway, that's known as a pure EMF. In future, we're going to assume that all batteries have a pure EMF, which I'm going to isolate from the rest of the battery's resistance and club the battery's internal resistance with any external resistance that might be present. And also we're going to assume that all the wires are ideal, and any resistance that the wires themselves carry also get clubbed into this single squiggly resistance. So that's our setup, and now this is just another differential equation that we need to now solve like we did in the previous case. So let's get doing that. The EMF E is going to be the voltage across the capacitor, which is Q over C by the definition of capacitance, and by Ohm's law that's I times R. So this is yet another differential equation. So this gives me E equals q over c plus r dq by dt, since current is none other than rate of change of charge. So this has a structure of a differential equation, except you notice that there's a constant term here. In the previous case, we did not have this, and so we could immediately write the solution down as a decaying exponential. Now we have to be a little more careful. So what I'll do here is I'll do a few rearrangements of these terms. So I'm going to get, first of all, there's nothing wrong with dividing the whole thing by r. So I'm going to get dq by dt. And if I divide by r, q over rc becomes q over the time constant is equal to e over r. All right. Now what I can do here is that I can think of the left-hand side and the right-hand side. So let me move all the non-derivative terms to the right-hand side. Now here we are stuck. This part cannot be separated any further, so we have to deal with the fact that this is going to go down for the ride. So I'm going to get dq divided by e over r minus q over tau is equal to dt. At this point, maybe we can perform a substitution. Let's do a U-substitution, and that U-substitution is that u equals e over r minus q over tau. Then du is minus dq over tau. So let's perform that substitution here, and I'll get the following equation. Well, if du is minus dq over tau, then dq equals minus tau du. So I'll write minus tau du divided by u equals dt. Now that's back to business. It just looks like an easy integral from this point on. So let's integrate both sides, and that gives you negative tau natural log of u. But natural log of u is just that, so I'll just rewrite that, e over r minus q over tau. I'll put an absolute value sign just to make sure it's always positive, and that's equal to t plus some constant, which I'll write again as const. Now we have to think about some conditions. Now I know that initially the capacitor had no charge, so certainly I can use that as my initial condition. Now, by the way, if this is not true, then you have to put the new initial conditions, and accordingly you will change your solution. So I just choose the simplest one. At t equals 0, q equals 0. So the capacitor is completely spent. It's like taking your cell phone that's already died and you're trying to charge it. So I get negative tau natural log of e over r, I don't have to put the absolute value signs, is equal to 0 plus constant, and that immediately tells us what the constant is. It's equal to that. Now I'll go back and substitute this up here. So I'll get negative tau natural log e over r minus q over tau equals t minus tau natural log of e over r. So clearly I can take a negative tau is sort of common to both terms, so I'll divide by negative tau. If I did that, I'll get natural log of e over r minus q over tau equals negative t over tau plus natural log of e over r. So now it's becoming more and more manageable. I'll move all the natural log terms to the left side and see what happens here. So this tells me that natural log of a minus natural log of b is natural log of a over b. So I'll write this as e over r minus q over tau divided by e over r. The whole absolute value sign on the whole thing is negative t over tau. Notice that units wise everything looks good. Tau is measured in time, t is measured in time, no units there either. Now take the exponential of both sides. So this tells me that e over r minus q over tau over e over r equals e to the minus t over tau. Similar exponential structure as in the decaying circuit. And now we have e over r minus q over tau equals e over r e to the minus t over tau, multiplying both sides by the denominator here. And now one or two more steps and we are done. So this is going to be the same as, just to quickly refresh, this means this leads to, one step leads to another, and this means that these two expressions are more or less the same. So we use this when we're trying to do busy work. So I get E over R times 1 minus e to the minus t over tau is equal to, now I've brought this to this side, so I have to take that to that side, so I'll get Q over tau. Now I'll write what tau is. It's R times C. So lastly, cancelling out the R's, I'm going to get Q equals EC times 1 minus e to the minus t over tau. Now, there's a special label given to E times C. It's called Q infinity. And the reason for that is this. The current is going to flow as long as the capacitor is still being charged. Once the capacitor gets the left side of the capacitor plate as the same voltage as the battery, the current will stop flowing. So the Q infinity, the charge of the capacitor at infinite time, is just going to be the voltage of the battery itself times the capacitance. So that's the logic behind that. So now we have the expression Q as a function of time equals Q infinity times 1 minus e to the minus t over tau. I will just focus on this graph. There are other graphs for voltage and current, etc. are shown in the notes to this video. I'll just focus on this one important graph, and that tells you how the charge changes with time. So here's Q and here's T, and we'll measure time as always in time constant units. Typically the time constant for a real capacitor and a real resistor are in the order of milliseconds, so it really happens very fast. For your rechargeable battery, it's of the order of minutes. So now you have also observe the time constant does not depend on how strong your battery is. So even if you nuke your cell phone with a very strong charger, it's not really going to make a difference. That's going to be your graph where Q infinity is the asymptote. You're never going to reach it, but in practice what's going to happen is that there'll be one electron less here, and so that's, you can't take a fraction of an electron, so that makes it practically charged. So the interpretation of the time constant now is a little bit complementary to the one we had before. So Q at a single value tau, single time constant, is going to be Q infinity times 1 minus e to the minus 1. Well, e to the minus 1 is already 37%, so that's going to be 63% of Q infinity. That's why I drew it pretty high up there. At 2 tau, it's going to be Q infinity 1 minus e to the minus 2. So that's going to be even bigger, like 85 or 90%. So that's already at 2 or 3 time constant is almost fully charged. So that's how the charging goes for this. Now, I also want to talk a little bit about the limits at t equal to 0 and t equal to infinity for both the charging and the discharging circuit. In this, for this particular circuit actually. So if I take the Q at 0, this one tells me that is equal to Q infinity 1 minus e to the 0. Well, e to the 0 is 1, so that's 0. And Q infinity is Q infinity. Okay? That's by definition, or you can just put the value infinity and you'll see that that's 0. So what does this really tell us? It tells us that at t equals 0, the cap behaves like a wire. The word wire in electrical engineering is called a short. So it behaves like a short or a wire. And at t equal to infinity, you'll notice, actually this is probably worth telling you, even though I'm not going to show you, the current in the circuit, even though the charge is building up, the current in the circuit is decaying. It's the initial current times e to the minus t over tau. And that makes sense because as the capacitor keeps getting charged, the current is going to have less and less reason to exist. So at t equal to infinity, the current will no longer flow. So how does the cap behave here? It behaves like a brick wall. And in electrical engineering, you don't say brick wall, it behaves like a gap. It's as though the circuit has been cut with a pair of scissors and no current flows. So these two are extremely useful limits to analyze the asymptotic nature of circuits in general.